What if I told you that the most powerful telescope humanity has ever built, a $10 billion machine floating 1.5 million kilometers from Earth, turned its golden eye toward our nearest galactic neighbor, and discovered something that made astronomers around the world pause, look at each other, and whisper the words, "This changes everything"? What if I told you that buried inside the Andromeda galaxy, hidden behind veils of cosmic dust that no telescope had ever been able to penetrate, there are secrets so profound, so unexpected, and so deeply unsettling that they force us to rethink not just how galaxies work, but how our own Milky Way came to be, how it will die, and what the ultimate fate of everything we have ever known truly looks like. What if I told you that the James Webb Space Telescope did not just take a pretty picture of Andromeda, but instead performed something closer to an autopsy on a living galaxy, peeling back layer after layer of cosmic history to reveal a story written in starlight, a story of violence, of consumption, of death, of rebirth, and of a collision so massive, so inevitable, and so terrifyingly close in cosmic terms that the first whispers of it are already reaching us right now, at this very moment, in the form of invisible dark matter tendrils that may already be intertwining with our own galaxy. Welcome. Welcome to a journey that is going to take you from the surface of this pale blue dot we call home, across 2.5 million light-years of empty void, and directly into the heart of a galaxy that contains 1 trillion stars. A galaxy that has been devouring its neighbors for billions of years. A galaxy that harbors a supermassive black hole so massive that it dwarfs our own Milky Way's central black hole by a factor of 50, and a galaxy that is right now, at this very second, hurtling toward us at a speed of 110 kilometers per second. That is nearly 400,000 kilometers per hour. That is a speed so incomprehensible that your brain cannot truly grasp it. And yet, compared to the vast distances involved, it is a crawl, a cosmic crawl that will take billions of years to close the gap. But make no mistake, the gap is closing, Andromeda is coming, and thanks to the James Webb Space Telescope, we now understand what that means in ways we never did before. In today's video, we are going to go deep, and when I say deep, I mean we are going to explore every single angle of this story, from the very first moment a human being looked up at the night sky and noticed a faint smudge of light that would one day be identified as an entire galaxy, all the way to the cutting-edge discoveries that the James Webb Space Telescope has made in just the past few years. We are going to understand what Andromeda truly is, not just as a pretty picture in a textbook, but as a dynamic, violent, evolving cosmic structure that holds within it the archaeological record of billions of years of galactic history. We are going to understand how the James Webb Space Telescope works, why its infrared vision is the key that unlocks secrets that were invisible to every telescope that came before it, including the legendary Hubble Space Telescope. We are going to walk through the actual discoveries, one by one, finding by finding, and I promise you, some of these will genuinely shock you. We are going to talk about ancient stars that are older than they should be, about the ghostly remnants of galaxies that Andromeda consumed and destroyed, about star-forming regions hidden behind impenetrable walls of cosmic dust, about a supermassive black hole that is sleeping but could awaken with terrifying consequences, about dark matter maps that reveal an invisible skeleton holding the galaxy together, and about the updated timeline for the inevitable collision between Andromeda and our Milky Way, a collision that will reshape everything we know. And here is something I need you to understand from the very beginning. This is not science fiction. Every single thing I'm about to tell you is based on real observations, real data, and real peer-reviewed science. The James Webb Space Telescope is not a fantasy. It is out there right now, orbiting the Sun at a point in space called L2, collecting photons that have traveled for millions of years across the void. Photons that carry within them the encoded history of the cosmos. And when those photons hit Webb's golden mirrors and are focused onto its incredibly sensitive detectors, they tell us stories. Stories about how the universe works. Stories about where we came from. And stories about where we are going. So, before we dive in, I want to ask you to do something. If you are someone who feels even a spark of curiosity about the universe, if you have ever looked up at the night sky and wondered what is out there, if you have ever felt that strange mix of awe and humility that comes from contemplating the sheer scale of existence, then this video was made for you. Hit that like button right now, subscribe to this channel if you have not already, and turn on that bell notification so you never miss another deep dive into the mysteries of the cosmos. Trust me, you are going to want to see what we have coming. But for now, for the next hour and a half or more, settle in, get comfortable, and prepare yourself for a journey that will change the way you see the night sky forever. Let us begin. To truly understand what the James Webb Space Telescope found when it peered inside Andromeda, we first need to understand what Andromeda actually is. And I do not mean some surface-level textbook definition. I mean, we need to genuinely grasp the scale, the history, the significance, and the sheer overwhelming majesty of this object. Because Andromeda is not just another galaxy, it is the galaxy. It is the nearest large galaxy to our own Milky Way. It is our cosmic twin, our mirror image, our rival, and ultimately our future partner in the most dramatic gravitational dance the local group of galaxies will ever witness. Andromeda, officially designated Messier 31, or M31, sits approximately 2.537 million light-years away from Earth. Now, let that number sink in for a moment. 2.5 million light-years. Light, which travels at 300,000 kilometers per second, the fastest speed anything in the universe can achieve, takes 2.5 million years to make the journey from Andromeda to your eyes. That means when you look at Andromeda, you are not seeing it as it is now. You are seeing it as it was 2.5 million years ago. You are looking back in time. And 2.5 million years ago on Earth, our ancestors, Homo habilis, were just beginning to use stone tools. The very first stirrings of what would eventually become human civilization were just appearing on the African savanna. And at that exact same moment, light was leaving Andromeda, beginning its impossibly long journey across the void, carrying with it information about a galaxy in a state that no longer exists. That light has been traveling ever since, through the expanding fabric of space itself, past countless other galaxies, through the cosmic web of dark matter filaments, through the local group, past the Triangulum galaxy, through the halo of our own Milky Way, through the interstellar medium, past stars and nebulae and planets we will never visit, until finally, after 2.5 million years of travel, it arrives at the mirror of the James Webb Space Telescope and tells us what Andromeda looked like when humanity was still climbing down from the trees. That is the timescale we are working with. That is the canvas on which this story is painted. Andromeda is a spiral galaxy, similar in many ways to our own Milky Way. It has a central bulge of older yellowish stars packed tightly together. It has sweeping spiral arms filled with younger, bluer stars, clouds of gas, and lanes of dark dust. It has a halo, a vast spherical region surrounding the disk, populated by ancient globular clusters, individual old stars, and an enormous amount of dark matter. But despite these structural similarities to our Milky Way, Andromeda is significantly larger. Its disk stretches approximately 220,000 light-years across. Our Milky Way, by comparison, is roughly 100,000 light-years in diameter. Andromeda is more than twice our size. And when it comes to stars, the numbers are staggering. Andromeda contains approximately 1 trillion stars. That is 1,000 billion. That is a 1 followed by 12 zeros. Our Milky Way, which itself contains a number of stars so large that most people cannot comprehend it, has somewhere between 200 billion and 400 billion stars. Andromeda has at least double that, possibly triple. Every single one of those trillion stars is a sun. Many of them have planets. Some of those planets sit in habitable zones where liquid water could exist. The mathematical probability of habitable worlds in Andromeda is enormous, and we will return to that thought later because it raises questions that are both thrilling and haunting. But Andromeda is not alone. It has its own entourage. Orbiting around it, like moons around a planet, are satellite galaxies. The most prominent of these are M32 and M110, both of which are visible in even amateur telescope images of Andromeda. M32 is a compact elliptical galaxy that sits very close to Andromeda's disk and has almost certainly been gravitationally distorted by its giant neighbor. M110 is a dwarf elliptical galaxy with a somewhat unusual nature, showing signs of recent star formation despite being classified as an elliptical, which typically have very little ongoing star formation. These satellite galaxies are important because they are part of Andromeda's gravitational kingdom, bound to it, orbiting it, and in some cases slowly being consumed by it. And, as we will see, the evidence of past consumption, past galactic cannibalism, is one of the most dramatic things the James Webb Space Telescope has revealed. Now, let me take you back in time, not 2.5 million years, but just over 1,000 years, to the first recorded observation of Andromeda by human eyes. In the year 964, a Persian astronomer named Abd al-Rahman al-Sufi was compiling his masterwork, a book called the Book of Fixed Stars, in which he meticulously documented the positions and appearances of stars visible to the naked eye. And in this book, al-Sufi described a small cloud in the constellation of Andromeda. He called it a nebulous smear. He had no idea what it was. He could not possibly have known that this tiny, faint patch of light was an entire galaxy containing 1 trillion stars sitting 2.5 million light-years away. To him, it was just a curious smudge in the sky. But that observation made over 1,000 years ago was the first recorded acknowledgement by any human being that Andromeda existed. It is a reminder that curiosity is the thread that connects all of human discovery. Al-Sufi looked up and wondered. And 1,000 years later, we pointed the most advanced telescope in history at the same smudge and uncovered secrets that would reshape our understanding of the cosmos. The story of Andromeda's scientific understanding took a dramatic leap forward in the early 20th century, during one of the most famous scientific disputes in history, an event known as the Great Debate. In 1920, 2 astronomers, Harlow Shapley and Heber Curtis, stood before the National Academy of Sciences in Washington, D.C., and argued about a question that sounds simple, but was in fact revolutionary. The question was this: are the so-called spiral nebulae, objects like Andromeda, located inside our own Milky Way galaxy, or are they separate, distant galaxies in their own right? Shapley argued that the Milky Way was the entire universe, that everything we could see was contained within it, and that the spiral nebulae were simply nearby clouds of gas. Curtis argued the opposite. He believed that the spiral nebulae were what he called island universes, independent galaxies far beyond the boundaries of our own. The debate was fierce, and it was not resolved that day. It took another 4 years and the brilliance of one of the greatest astronomers who ever lived to settle the question once and for all. In 1924, Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory in California to observe Andromeda. And what he did was extraordinary. He identified a particular type of star within Andromeda called a Cepheid variable. Cepheid variables are stars that pulsate, brightening and dimming in a regular cycle. And here is the crucial point. There is a direct relationship between the period of a Cepheid's pulsation and its intrinsic luminosity. If you know how bright a Cepheid truly is, and you measure how bright it appears from Earth, you can calculate how far away it is. It is like knowing the wattage of a light bulb and using its apparent brightness to figure out how far away the lamp is. Hubble found Cepheid variables in Andromeda and used them to calculate its distance. The result was staggering. Andromeda was far, far beyond the boundaries of the Milky Way. It was not a nebula within our galaxy. It was an entirely separate galaxy, an island universe, just as Curtis had argued. And in that single discovery, the known universe expanded by a factor of billions. Literally overnight, humanity went from thinking the Milky Way was everything, was the entire cosmos, to realizing that our galaxy was just one among what would eventually turn out to be hundreds of billions or even trillions of galaxies spread across an observable universe 93 billion light-years in diameter. Andromeda was the key. Andromeda was the galaxy that unlocked the true scale of the universe, and that is why it holds such a special place in the history of astronomy. From that moment forward, Andromeda became one of the most studied objects in the sky. Every major telescope, every new observational technology, every advance in astronomical instrumentation was at some point directed toward Andromeda. And for good reason. You see, there is a fundamental problem with studying our own Milky Way. We are inside it. Trying to understand the structure and properties of the Milky Way from within is like trying to understand the layout of an entire city while standing in a single room of a single building. You can look out the windows and see parts of the city, but you can never see the whole thing at once. You cannot get the bird's-eye view. But Andromeda? Andromeda is like looking at a city from a hilltop. We can see the whole thing. We can see its spiral arms, its central bulge, its dust lanes, its satellite galaxies, its halo. We can study it as a complete system in a way that we can never study our own galaxy. And because Andromeda is structurally similar to the Milky Way, everything we learn about Andromeda teaches us something about our own home. Andromeda is our mirror. It shows us what we might look like from the outside. But Andromeda is more than a mirror. It is also a laboratory. It is a place where we can study the processes that shape galaxies, star formation, stellar evolution, galactic dynamics, the role of dark matter, the influence of supermassive black holes, the effects of galaxy mergers and interactions. Every one of these processes operates in Andromeda, and because it is close enough to resolve individual stars and structures, we can study these processes in extraordinary detail. No other large galaxy offers us this combination of proximity, similarity to our own galaxy, and scientific richness. Andromeda is, in many ways, the most important galaxy in the sky other than our own. And then there is the elephant in the room. Or, perhaps I should say, the galaxy in the sky, because the single most dramatic fact about Andromeda is one that has captured the public imagination like few other astronomical discoveries ever have. Andromeda is on a collision course with the Milky Way. It is heading straight for us. At a speed of approximately 110 kilometers per second, Andromeda is closing the gap between our two galaxies with every passing moment. In roughly 4 to 5 billion years, depending on which model you use, Andromeda and the Milky Way will collide. They will merge. They will become one. Two great spiral galaxies, each with their own histories, their own stars, their own planets, their own possible civilizations, will be reshaped, disrupted, and ultimately fused into a single, massive elliptical galaxy that astronomers have playfully dubbed Milkomeda or Milkdromeda. This is not speculation. This is not a possibility. This is a near certainty based on decades of observations, measurements of Andromeda's velocity and trajectory, and sophisticated computer simulations that model the gravitational interactions of billions of stars. The collision is coming. And as we will see, the James Webb Space Telescope has given us new information that refines our understanding of exactly how and when this cosmic merger will unfold. So that is Andromeda, a galaxy of 1 trillion stars, a galaxy 2.5 million light-years away, a galaxy that was the key to unlocking the true scale of the universe, a galaxy that serves as our cosmic mirror and our most important galactic laboratory, a galaxy that has consumed and destroyed smaller galaxies throughout its history, a galaxy that harbors a supermassive black hole 50 times more massive than our own, and a galaxy that is heading straight for us at a speed that defies human comprehension. That is what the James Webb Space Telescope pointed its instruments at. And what it found shook the foundations of what we thought we knew. But before we get to the discoveries, we need to understand the instrument that made them possible. We need to understand the James Webb Space Telescope, and I do not just mean a surface-level overview. I mean we need to genuinely appreciate the engineering marvel, the scientific breakthrough, and the sheer audacity of human ambition that this telescope represents. Because JWST is not just a telescope, it is arguably the single most complex and capable scientific instrument that human civilization has ever created, and without understanding how it works and why it is different from everything that came before, the significance of its Andromeda discoveries cannot be fully appreciated. The James Webb Space Telescope was launched on December 25, 2021, Christmas Day. And that is fitting, because for astronomers around the world, it was the greatest gift imaginable. After more than 25 years of development, countless setbacks, budget overruns that saw the project's cost balloon from an original estimate of around $1 billion to a final price tag of approximately $10 billion, and technical challenges so daunting that many doubted the telescope would ever fly. JWST finally lifted off aboard an Ariane 5 rocket from the Guiana Space Center in French Guiana. And from the moment of launch, it had to execute perfectly. There was no room for error. Unlike the Hubble Space Telescope, which orbits the Earth at a relatively accessible altitude of about 540 kilometers and could be serviced by space shuttle missions, JWST was heading to a destination so far away that no spacecraft currently in existence could reach it for repairs. It was heading to the second Lagrange point, or L2, a gravitationally stable point in space located approximately 1.5 million kilometers from Earth, on the side opposite the Sun. At L2, the gravitational pull of the Earth and the Sun combine in such a way that the telescope orbits the Sun at the same rate as the Earth, effectively staying in a fixed position relative to our planet while keeping the Sun, Earth, and Moon all behind it. This is critical because JWST observes in infrared light, and infrared is essentially heat radiation. To detect the incredibly faint infrared signals from distant cosmic objects, the telescope itself must be extraordinarily cold. Any heat from the Sun, Earth, or Moon would blind its detectors. So JWST carries an enormous sun shield, roughly the size of a tennis court, made of 5 layers of a material called capton, each thinner than a human hair. This sun shield blocks the heat from the Sun and keeps the telescope's instruments at a temperature of about minus 233 degrees Celsius, just 40 degrees above absolute zero, On the sun-facing side, the temperature can reach as high as 85 degrees Celsius. So, across the 5 layers of this sun shield, there is a temperature difference of over 300 degrees. That is the engineering precision we are talking about. The telescope's primary mirror is 6.5 meters in diameter, composed of 18 individual hexagonal segments made of beryllium and coated in a microscopically thin layer of gold. Gold is used because it is an excellent reflector of infrared light. These 18 segments had to be folded up to fit inside the rocket's fairing during launch, and then unfolded and precisely aligned in space, with each segment's position controlled to an accuracy of less than 1/10,000th the thickness of a human hair. The total collecting area of this mirror is approximately 25 square meters, compared to Hubble's 4.5 square meters. That means JWST can collect roughly 6 times more light than Hubble. But the advantage goes far beyond just light-gathering power. The real revolution of JWST is its wavelength range. The Hubble Space Telescope primarily observes in visible light and ultraviolet, with some limited capability in the near-infrared. It shows us the universe as our eyes would see it if our eyes were enormously more powerful. And Hubble's images are stunning. Its view of Andromeda, captured in 2015, is one of the most famous astronomical images ever taken. A mosaic of over 1.5 billion pixels, showing over 100 million individual stars in a portion of Andromeda's disk. That image was, at the time, the sharpest and most detailed view of another galaxy ever obtained. But even Hubble, for all its power, has a fundamental limitation. Visible light cannot penetrate dust, and galaxies are full of dust. Enormous clouds of microscopic solid particles, made of silicates, carbon compounds, and ice, pervade the disks and spiral arms of galaxies like Andromeda. These dust clouds are opaque to visible light. They absorb it and scatter it. When Hubble looks at a dusty region of Andromeda, it sees a dark lane, a void, an absence. It is like trying to see through a fog bank. You know there is something on the other side, but you cannot see it. This is where JWST changes everything. JWST observes primarily in infrared light, at wavelengths ranging from about 0.6 micrometers, which is at the red end of visible light, out to 28.5 micrometers, which is deep into the mid-infrared. And the critical property of infrared light is that it passes through dust. Those same dust clouds that are opaque barriers to Hubble are essentially transparent to JWST. Infrared light has longer wavelengths than visible light, and these longer wavelengths can slip past the tiny dust grains that block shorter wavelength visible photons. It is like the difference between trying to throw a basketball through a chain-link fence versus throwing a marble. The longer wavelength infrared photons pass through the gaps between the dust grains, while the shorter wavelength visible photons get caught. This means JWST can see things that Hubble literally cannot. It can peer inside the dense dust clouds where stars are being born. It can see through the dusty central regions of galaxies to study the stars and structures hidden within. It can detect the faint infrared glow of cool objects that emit little or no visible light. Objects like brown dwarfs, cool exoplanets, and ancient dying stars. And it can see the most distant objects in the universe, objects whose light has been so stretched by the expansion of space that it has shifted from its original ultraviolet or visible wavelengths all the way into the infrared, a phenomenon called redshift. Every single one of these capabilities is relevant to studying Andromeda, and taken together they make JWST an unprecedented tool for understanding our nearest galactic neighbor. JWST carries 4 main scientific instruments, each designed for a specific set of observations. The first is NIRCam, the near-infrared camera, which is the telescope's primary imager. NIRCam captures images in the near-infrared, at wavelengths between 0.6 and 5 micrometers. It produces stunningly detailed images with incredible resolution and sensitivity, and it is the instrument responsible for many of the breathtaking images that have made JWST famous around the world. The second is NIR-SPEC, the Near-Infrared Spectrograph, which does not take pictures in the traditional sense but instead splits the light from objects into its component wavelengths, creating a spectrum. A spectrum is like a fingerprint. It reveals the chemical composition of an object, its temperature, its density, its velocity, and many other physical properties. NIR-SPEC has a particularly revolutionary capability. It can take spectra of up to 100 objects simultaneously using an array of tiny configurable shutters called a microshutter array. This is enormously efficient and allows astronomers to characterize the properties of hundreds of stars or galaxies in a single observation. The third instrument is MIRI, the mid-infrared instrument, which observes at longer wavelengths between 5 and 28 micrometers. MIRI can see even cooler objects and penetrate even thicker dust than the near-infrared instruments. It is particularly useful for studying dust structures, planetary systems, and the chemistry of interstellar material. MIRI requires an additional active cooling system, a cryocooler, to bring its detectors down to a temperature of just 7 degrees above absolute zero, because at mid-infrared wavelengths, even the slight warmth of the telescope structure would overwhelm the faint signals from space. The fourth instrument is FGS/NIRISS, which combines a fine guidance sensor for precisely pointing the telescope with a near-infrared imager and slitless spectrograph that provides additional imaging and spectroscopic capabilities. Together, these four instruments give JWST a toolkit of extraordinary versatility. It can image objects with unprecedented sharpness and sensitivity across a wide range of infrared wavelengths. It can analyze the chemical composition and physical properties of those objects through spectroscopy. It can penetrate dust barriers that have blocked our view for centuries. And it can do all of this from its perch at L2, 1.5 million kilometers from Earth, in the cold silence of space, undisturbed by the atmosphere, undisturbed by light pollution, undisturbed by the thermal noise that plagues ground-based observatories. Now, you might be wondering, if JWST is designed to study the most distant objects in the universe, to look back 13 billion years in time to see the first galaxies forming after the Big Bang, then why would it bother looking at Andromeda? Andromeda is right next door in cosmic terms. It is like having the world's most powerful microscope and using it to look at something on your desk instead of studying exotic microorganisms. But this is actually a misunderstanding of how JWST is used and why Andromeda is such a valuable target. The truth is that JWST is not just a deep-field telescope. It is a general-purpose observatory, designed to study everything from planets in our own solar system to the most distant galaxies in the observable universe. And Andromeda occupies a unique sweet spot that makes it one of the most scientifically valuable targets for JWST. Here is why. When JWST observes very distant galaxies, those galaxies are so far away that even JWST cannot resolve their individual stars. It sees them as smudges of light, and while it can extract an enormous amount of information from that light through spectroscopy and careful analysis, it cannot study the galaxy's internal structure in fine detail. It cannot count individual stars, measure their properties one by one, or trace the detailed patterns of dust and gas within them. But Andromeda is close enough that JWST can do all of these things. JWST can resolve individual stars in Andromeda, measure their brightnesses, determine their colors, estimate their ages and chemical compositions, and track their movements. It can map the dust structures within Andromeda's spiral arms with exquisite detail. It can study the environment around Andromeda's supermassive black hole. And crucially, because Andromeda is a large, massive, spiral galaxy, similar to the ones JWST observes in the distant universe, everything we learn about Andromeda in close-up detail can be applied to interpreting the more distant, less detailed observations of galaxies billions of light-years away. Andromeda serves as a Rosetta Stone, a key that helps us decode the information embedded in the light from galaxies across the entire observable universe. Multiple scientific programs have been dedicated to JWST observations of Andromeda, and the results have been nothing short of revolutionary. Let me take you through them, finding by finding, discovery by discovery. And I want you to pay attention because some of what I'm about to tell you is going to challenge things you thought you knew about how galaxies work, how our cosmic neighborhood is structured, and what the future holds for our own Milky Way. Let us begin with the stars. When JWST turned its infrared eyes toward Andromeda, one of the first and most immediate results was the sheer improvement in our ability to resolve individual stars in regions that had previously been impenetrable. Consider Andromeda's central bulge, the dense concentration of stars at the very center of the galaxy surrounding the supermassive black hole. In visible light, as seen by Hubble, this region is incredibly crowded. Billions of stars are packed into a relatively small volume, and at Hubble's resolution and wavelength, the stars blur together into a smooth, golden glow. Individual stars are difficult or impossible to pick out, especially in the dustier regions. But JWST, operating in the infrared, can not only see through the dust but also benefits from the fact that many of the stars in the bulge are cool, red, and old, meaning they emit most of their light in the infrared. These stars practically leap out of JWST's images. For the first time, astronomers could resolve individual stars in the inner regions of Andromeda's bulge with a clarity that was simply not possible before. Imagine going from seeing a forest as a single green mass on a distant hillside to suddenly being able to count individual trees, identify their species, and estimate their ages. That is the scale of improvement we are talking about. But it was not just the ability to see more stars that was significant. It was what those stars told us. You see, stars are not just points of light. Each star is a record keeper, a fossil, a time capsule that preserves information about the conditions under which it was born. The key piece of information is something astronomers call metallicity. In astronomy, the word metals refers to every element heavier than hydrogen and helium. So, carbon, oxygen, nitrogen, silicon, iron, gold, uranium, everything that is not hydrogen or helium is a metal in astronomical terms. And the metallicity of a star, the fraction of its mass that consists of these heavier elements, tells you something crucial about when and where that star formed. Here is why. In the very early universe, just after the Big Bang, the only elements that existed were hydrogen, helium, and trace amounts of lithium. There was nothing else, no carbon, no oxygen, no iron. All of those heavier elements were created later, inside the cores of stars, through the process of nuclear fusion, and then scattered into space when those stars exploded as supernovae or shed their outer layers as they died. The next generation of stars formed from gas that was enriched by these heavier elements. And when those second-generation stars lived and died, they added even more metals to the mix. Each generation of stars enriches the interstellar medium with more and more heavy elements. So, a star with very low metallicity, one that contains very few heavy elements, must have formed very early in cosmic history, before many generations of stars had lived and died. A star with high metallicity, rich in heavy elements formed later, from gas that had been enriched by many previous generations. Metallicity is a cosmic clock. JWST's spectroscopic capabilities, particularly with NIR spec, allowed astronomers to measure the metallicities of large numbers of individual stars across different regions of Andromeda, and the results painted a picture that was both expected in some ways and deeply surprising in others. As anticipated, stars in Andromeda's central bulge tended to have relatively high metallicities, consistent with this being a region where many generations of star formation had occurred, recycling and enriching the gas over billions of years. Stars in the outer halo of Andromeda tended to have lower metallicities, consistent with these being older stars that formed earlier in the galaxy's history. This basic gradient from high metallicity in the center to low metallicity in the outskirts was expected and matched theoretical predictions. But then, JWST found the anomalies. In certain regions of Andromeda's halo, JWST detected populations of stars with extremely low metallicities. These were stars that appeared to be among the oldest in the entire universe, stars that formed within the first 1 to 2 billion years after the Big Bang, over 12 billion years ago. And here is what made this surprising. The presence of such ancient metal-poor stars in Andromeda's halo is not itself unusual. We expect to find old stars in galaxy halos, but the sheer number of them, their spatial distribution, and their specific chemical signatures did not match the predictions of standard models for how Andromeda formed and assembled. Some of these ancient stars appeared to be clustered in ways that suggested they did not form in Andromeda itself. They were immigrants. They were born in other smaller galaxies that were later consumed by Andromeda, their stars stripped away and absorbed into Andromeda's halo. And the chemical fingerprints of these stars, the specific ratios of different elements they contained, allowed astronomers to begin identifying which stars came from which consumed galaxy. It was like performing a DNA test at a crime scene and identifying the victims. Except in this case, the crime scene was an entire galaxy, and the victims were other galaxies that Andromeda had destroyed. This brings us to one of the most dramatic and deeply fascinating aspects of what JWST revealed about Andromeda: galactic cannibalism. The evidence that Andromeda is, and has been for billions of years, a predator, a cosmic giant that grows by consuming its smaller neighbors. Now, the concept of galactic cannibalism was not new. Astronomers had known for decades that large galaxies like Andromeda and our own Milky Way grow partly by merging with and absorbing smaller galaxies. The evidence was already there in the form of tidal streams, long, thin arcs of stars that trace the paths of disrupted galaxies, like the trails of debris left behind as a smaller galaxy is torn apart by the gravitational tides of a larger one. Andromeda's most famous tidal stream, the giant stellar stream, was discovered in 2001 and is a massive arc of stars stretching across the halo, believed to be the remnant of a dwarf galaxy that was consumed approximately 2 billion years ago. Hubble and ground-based telescopes had mapped several of these streams around Andromeda, providing clear evidence of past mergers. But JWST took this to an entirely new level. Its deep infrared imaging revealed stellar streams and substructures in Andromeda's halo that had never been seen before. Streams that were too faint, too obscured by dust, or too diffuse for previous telescopes to detect. JWST essentially provided a higher resolution, more sensitive, and more complete map of the archaeological evidence buried in Andromeda's halo. And when astronomers analyzed these newly discovered streams and substructures, combining JWST imaging with spectroscopic data on the ages and metallicities of the stars within them, a picture emerged of a galaxy with a far more violent and active merger history than had previously been appreciated. The data suggests that Andromeda may have consumed somewhere between 10 and 20 smaller galaxies over the course of its lifetime. Each of these merger events left behind a distinct signature, a stream of stars with its own characteristic age, metallicity, and orbital path around Andromeda. Some of these mergers happened in the distant past, more than 8 or 10 billion years ago, when the universe was young and galaxy interactions were more common. Others happened more recently, within the last 2 to 3 billion years. Each one added mass to Andromeda, contributed stars to its halo, and may have triggered episodes of star formation or disturbed the structure of its disk. The giant stellar stream, previously the best studied of these remnants, was re-examined with JWST data that revealed finer details of its stellar population. The stars in the stream showed a range of metallicities and ages that helped pinpoint the properties of the galaxy that was destroyed. A moderately sized dwarf galaxy that Andromeda consumed approximately 1.8 to 2 billion years ago. JWST's precision allowed astronomers to estimate not just when this merger happened, but the approximate mass, size, and star formation history of the galaxy that was consumed. It was like reconstructing the profile of a missing person from the wreckage they left behind. But perhaps the most intriguing discovery in this vein was evidence that Andromeda experienced one or more major mergers earlier in its history. Events in which a relatively large galaxy, not just a dwarf galaxy but something more substantial, was consumed and integrated. The evidence for this comes from the properties of stars in Andromeda's inner halo and thick disk, regions where JWST's infrared vision provided new insights. The kinematics of these stars, their motions and orbits, combined with their chemical signatures, suggest that a significant merger event occurred somewhere around 8 to 10 billion years ago. This would have been a formative event for Andromeda, one that may have helped shape its present-day structure, influence the growth of its central bulge, and possibly even fed material to its supermassive black hole. The idea that Andromeda experienced a major merger in its past is not new. It had been proposed based on earlier data, but JWST provided the most detailed and compelling evidence yet. It is like finding the murder weapon after years of circumstantial evidence. The case for Andromeda as a galactic cannibal, one that has consumed both small and moderately large galaxies over billions of years, is now stronger than ever. And here is the thing that should give you chills. Our own Milky Way has done the same thing. Right now, at this very moment, the Milky Way is in the process of consuming the Sagittarius Dwarf Elliptical Galaxy, a small galaxy that orbits within our galaxy's halo and is being gradually torn apart by our gravitational tides. We have consumed others in the past, too. The remnant of a galaxy nicknamed Gaia Enceladus, or the Gaia Sausage, was consumed by the Milky Way approximately 10 billion years ago, and its stars are now dispersed throughout our halo. We are not innocent. We are predators too. And in the grand cosmic narrative, the biggest act of galactic consumption is yet to come, when Andromeda and the Milky Way, two great predators of the local group, finally collide and consume each other. But we will return to that later. Now, let me shift our focus to another remarkable set of JWST discoveries. While the ancient stars and tidal streams tell us about Andromeda's past, the dust and star-forming regions tell us about its present and future. Andromeda is not a dead galaxy. It is not a static, unchanging structure. It is alive, dynamic, and actively forming new stars. And JWST's infrared vision revealed the details of this ongoing star formation with a clarity that was simply impossible before. One of the most striking features of Andromeda when viewed in the infrared is its ring structure. Andromeda has a series of concentric rings of dust and star formation activity that are prominently visible in infrared images. The most prominent of these is a ring at a radius of about 10 kiloparsecs, roughly 32,000 light-years from the center. This ring was known before JWST, having been observed by previous infrared telescopes like the Spitzer Space Telescope. But JWST's MIRI instrument revealed this ring and the surrounding dust structures in unprecedented detail. The ring glows brightly in the mid-infrared, indicating warm dust heated by the ultraviolet radiation from young, massive stars embedded within it. The dust structures are not smooth or uniform. They are complex, filamentary, knotted, and layered, showing a level of fine scale structure that previous telescopes could not resolve. But here is what makes Andromeda's ring structure truly fascinating, and what JWST has helped to clarify. These rings are not a natural equilibrium feature of a spiral galaxy. They are believed to be the result of a gravitational disturbance, specifically a close encounter with one of Andromeda's satellite galaxies. The leading theory, supported by detailed computer simulations, is that M32, the compact elliptical satellite galaxy that appears projected against Andromeda's disk in our images, actually passed through or very close to Andromeda's disk approximately 200 million years ago. This close encounter sent gravitational shock waves rippling through Andromeda's disk, like dropping a stone into a pond. These waves compressed the gas and dust in Andromeda, triggering waves of star formation that propagated outward from the point of impact in expanding rings. The ring structure we see today is the frozen record of this impact, a snapshot of the expanding wave of star formation still propagating through the galaxy hundreds of millions of years after the initial disturbance. JWST's detailed infrared observations of these rings provided new constraints on the timing and nature of this interaction. By measuring the ages and properties of the young stars within the rings, astronomers can refine their estimates of when the disturbance occurred and how it propagated through the disk. The data suggests that the interaction with M32 was not a single event but possibly a series of close passages, as M32 orbits within and around Andromeda's disk on a complex trajectory. Each passage would have sent its own set of shock waves through the disk, creating the multiple ring structure we observe. And JWST's ability to see through the dust means it can map these rings completely, including the portions that are hidden behind the densest dust lanes in visible light. Beyond the rings, JWST uncovered individual star-forming regions deep within Andromeda's dust clouds that were completely invisible to Hubble and other optical telescopes. These are regions where cold molecular gas is collapsing under its own gravity, fragmenting into dense cores and forming new stars. The youngest of these stars, the protostars, are still enshrouded in the gas and dust from which they are forming. They have not yet ignited hydrogen fusion in their cores, or they have only recently done so. In visible light, these objects are completely hidden, but in the infrared, they shine. The warm dust surrounding them glows brightly as it absorbs the protostar's radiation and re-emits it at longer wavelengths. JWST's NIR-CAM and MIRI instruments can see these embedded protostars and study them in detail, measuring their luminosities, temperatures, and the properties of the surrounding dust and gas. What astronomers found was that the rate and efficiency of star formation in some of these deeply embedded regions differed from what standard models predicted. In some areas, star formation appeared to be more efficient than expected, with a higher fraction of the available gas being converted into stars. In other areas, star formation seemed suppressed, with large reservoirs of dense gas that had not yet collapsed to form stars. The reasons for these variations are still being investigated, but they likely relate to local conditions such as the magnetic field structure, the turbulence in the gas, the influence of nearby massive stars and their radiation, and the overall dynamics of the region. Understanding these variations is crucial because the rate of star formation determines how quickly a galaxy converts its raw material into stars, which in turn affects the galaxy's luminosity, color, chemical evolution, and long-term fate. JWST also produced the most detailed infrared dust map of Andromeda ever created. Dust, as I mentioned earlier, is a crucially important component of galaxies. It may constitute only about 1% of the total mass of the interstellar medium, with gas making up the rest, but its effects are disproportionately large. Dust absorbs and scatters visible light, reshaping the appearance of galaxies. It re-emits the absorbed energy as infrared radiation, making dusty regions bright in the infrared. It provides surfaces on which molecules can form, including complex organic molecules, and it participates in the process of star formation, helping gas clouds cool and collapse. By mapping the dust in Andromeda in detail, JWST provides insights into all of these processes. The dust map revealed a complex, multi-layered structure. Dust is concentrated in Andromeda's spiral arms and the ring structures, as expected, but it also extends into inter-arm regions and even into the inner halo in unexpected ways. The filamentary structure of the dust, with long thin threads and sheets interspersed with cavities and bubbles, reflects the dynamic environment of the interstellar medium, shaped by stellar winds from massive stars, supernova explosions, and the overall rotation and turbulence of the galactic disk. JWST's MIRI instrument also mapped the emission from polycyclic aromatic hydrocarbons, or PAHs, in Andromeda. PAHs are complex organic molecules consisting of multiple carbon rings with attached hydrogen atoms. They are the most complex molecules commonly found in the interstellar medium and are considered potential building blocks for prebiotic chemistry. The PAH emission map traces the distribution of these molecules across Andromeda and reveals how they are affected by the local radiation environment. In regions of intense ultraviolet radiation near massive young stars, PAHs are destroyed, creating holes in the PAH emission map. In more shielded regions, PAHs thrive. This provides a detailed picture of the interplay between star formation and the chemistry of the interstellar medium in Andromeda. JWST also identified numerous planetary nebulae scattered throughout Andromeda. Planetary nebulae are the glowing shells of gas ejected by dying stars of low to intermediate mass, stars roughly similar to our own Sun. When such a star reaches the end of its life, it expands into a red giant, its outer layers becoming loosely bound. Eventually, these outer layers are ejected into space, forming a beautiful, expanding shell of glowing gas. The hot core of the star, now exposed, is called a white dwarf, and its intense ultraviolet radiation ionizes the ejected gas, causing it to glow. Planetary nebulae are brief, transient phenomena in cosmic terms, lasting only about 10 to 20,000 years before the gas dissipates into the interstellar medium. But they are scientifically important because they represent one of the main channels through which stars returned processed material, enriched with heavy elements, to the interstellar medium, material that will be incorporated into the next generation of stars. JWST's observations identified planetary nebulae in Andromeda, and, through spectroscopy, measured the chemical compositions of their ejected shells. This provides direct information about what elements are being recycled back into Andromeda's interstellar medium and at what rates. some of the planetary nebulae showed unusual chemical compositions that suggest they originated from binary star systems, where the interaction between two stars affects the final stages of stellar evolution and the composition of the ejected material. This is a level of detail that was extremely difficult to achieve with previous telescopes and adds another layer to our understanding of the chemical evolution of Andromeda. Let me pause here for a moment and let you absorb what we have covered so far. JWST has revealed ancient stars in Andromeda that are among the oldest in the universe. It has uncovered the ghosts of at least 10 to 20 smaller galaxies that Andromeda consumed over billions of years. It has mapped the ring structures created by gravitational interactions with satellite galaxies. It has penetrated dust clouds to reveal hidden star-forming regions. It has created the most detailed dust and chemical map of Andromeda ever. And it has identified and characterized the dying stars returning their enriched material to the galaxy. Each of these findings is significant on its own. Together, they paint a picture of a galaxy that is extraordinarily complex, dynamic, and layered with history. But we are not done, not by a long way, because we have not yet talked about what JWST found at the very heart of Andromeda, in the domain of the supermassive black hole. Let me take you there now. At the very center of the Andromeda galaxy, nestled within the dense concentration of stars that forms the galactic bulge, there lurks a monster. It is a supermassive black hole, designated M31 star, a designation that follows the convention used for our own galaxy's central black hole, Sagittarius A star. But while Sagittarius A star is itself an impressive object, with a mass of approximately 4 million times that of our Sun, M31 star is in a different league entirely. Estimates of its mass range from 100 million to 230 million solar masses. That means Andromeda's central black hole is somewhere between 25 and 50 times more massive than our own. It is an absolute behemoth, a gravitational singularity with a region of no return, an event horizon that would engulf our entire solar system if placed at the Sun's location. And yet, despite its enormous mass, M31 star is astonishingly quiet. It is what astronomers call a quiescent supermassive black hole. It is not actively consuming large amounts of material. It is not surrounded by a blazing accretion disk of superheated gas spiraling inward at near light speed. It is not launching relativistic jets of plasma thousands of light years into space. By the standards of active galactic nuclei, those distant galaxies whose central black holes are voraciously feeding and outshining all the billions of stars in their host galaxies combined, M31 star is practically asleep. It is a sleeping giant. And understanding why it is sleeping, what it did when it was awake, and what could wake it up again are some of the most fascinating questions in extragalactic astronomy. JWST's infrared observations of Andromeda's center provided new insights into the environment around M31 star. Previous observations, including those by Hubble, had revealed that Andromeda has a peculiar double nucleus. When imaged at high resolution, the center of Andromeda does not show a single bright peak, but rather two distinct concentrations of light, separated by a small distance. This was first observed clearly by Hubble in the early 1990s, and initially caused confusion. Does Andromeda have two central black holes? Is it the result of a merger that is not yet fully completed? The answer, worked out through careful analysis and modeling, is more subtle and more interesting. One of the two brightness peaks, called P1, is not the true center of the galaxy. It is a concentration of stars in an eccentric orbit around the actual center. The true center, called P2, coincides with the location of the supermassive black hole. The reason P1 appears brighter than P2 is that the stars in their eccentric orbit spend more time near the far point of their orbit, moving more slowly as they loop around, creating a pileup, a concentration that appears as a bright spot offset from the true center. This is an effect predicted by orbital mechanics, and it means that the double nucleus is actually a single nucleus with a peculiar orbital structure. JWST's new infrared observations revealed finer structure within this double nucleus that had not been seen before. The higher resolution and infrared sensitivity allowed astronomers to peer deeper into the dust that partially obscures the central region and to resolve the stellar population in greater detail. The data showed that the stellar dynamics near the center are even more complex than previous models had predicted. There appear to be multiple distinct kinematic components, groups of stars moving in different ways, suggesting a layered structure that may have been built up through multiple episodes of accretion and merging over Andromeda's history. Some of the stars very close to the black hole are moving at extraordinary speeds, hundreds of kilometers per second, whipped around by the intense gravitational field. By measuring these velocities with JWST's spectroscopic instruments, astronomers were able to refine the mass estimate of M31 star with greater precision than ever before, helping to narrow down exactly how massive this sleeping giant truly is. The environment around M31 star also showed signs of its past activity. While the black hole is currently quiescent, it was not always so. JWST detected warm dust structures in the vicinity of the black hole that may be remnants of past feeding episodes. When a supermassive black hole actively accretes material, the intense radiation it produces can heat, ionize, and reshape the surrounding gas and dust, creating structures that persist long after the feeding stops. The warm dust detected by JWST's MIRI instrument in the inner regions of Andromeda may be the lingering echo of a time when M31 star was actively feeding, perhaps triggered by a gas inflow from a past merger event. This is consistent with the evidence from stellar streams that Andromeda experienced a significant merger somewhere around 2 billion years ago. It is plausible that this merger event not only disrupted the consumed galaxy and left behind the giant stellar stream, but also funneled gas toward the center of Andromeda, temporarily reactivating the black hole before the fuel supply was exhausted, and M31 star returned to its slumber. The comparison between M31 star and our own Sagittarius A star is illuminating. Both are supermassive black holes at the centers of large spiral galaxies. Both are currently quiescent, but M31 star is far more massive. Why? The mass of a central supermassive black hole is known to correlate with properties of its host galaxy, particularly the mass and velocity dispersion of the central bulge of stars. More massive bulges tend to harbor more massive black holes. Andromeda has a larger and more massive central bulge than the Milky Way, so it makes sense that its black hole is more massive. But the details of how M31 star grew to its current mass are still being worked out. Did it grow primarily through gas accretion, swallowing material funneled toward the center by galaxy dynamics and mergers? Did it grow through the merger of smaller black holes brought in by consumed galaxies? JWST's observations contribute to answering these questions by constraining the merger history of Andromeda, which directly affects the growth history of its central black hole. One of the most tantalizing questions is what could reawaken M31 star, and the answer is a large inflow of gas to the central region. If a significant amount of gas were to fall toward the center of Andromeda, M31 star could begin actively accreting again. It could develop an accretion disk, produce intense radiation, and potentially launch jets. It could transition from a quiescent black hole to an active galactic nucleus. And the most obvious future source of such a gas inflow is the collision with the Milky Way. When Andromeda and the Milky Way collide and merge in approximately 4 to 5 billion years, the gravitational disruption will send shock waves through both galaxies, compressing gas clouds, triggering massive bursts of star formation, and funneling gas toward the central regions. It is entirely possible that both M31 star and Sagittarius A star could be reactivated by this event. The merged galaxy could briefly become an active galaxy, with one or both central black holes blazing with the fury of an active galactic nucleus. Eventually, the two black holes would spiral toward each other, form a binary system, and merge into a single, even more massive black hole at the center of the new combined galaxy. That merger would release an enormous burst of gravitational waves, ripples in the fabric of space-time itself, that would propagate outward through the universe at the speed of light. JWST has also observed other galaxies in various stages of merging. Galaxies far more distant than Andromeda, but caught in the act of colliding and combining. These observations serve as analogs, previews of what will happen when Andromeda and the Milky Way merge. By studying these merging systems, astronomers can see the various stages of the process: the initial tidal disruption, the triggered star formation, the central activity, and the eventual relaxation into a new, merged structure, and compare what they see with simulations of the Milky Way and Andromeda merger. The agreement between observations and simulations gives astronomers confidence that their models of galaxy merging are broadly correct, and that their predictions for our own future merger are reliable. Let me also talk about one of the most subtle and profound aspects of JWST's Andromeda observations, one that deals not with what we can see but with what we cannot. I am talking about dark matter. Dark matter is one of the deepest mysteries in modern physics. We know it exists because we can see its gravitational effects. Galaxies rotate faster than they should if the only matter present were the visible stars, gas, and dust. Galaxy clusters hold together despite having far too little visible mass to gravitationally bind them. The large-scale structure of the universe, the cosmic web of filaments and voids, matches the predictions of simulations that include vast amounts of dark matter, and the pattern of tiny temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, can only be explained if dark matter makes up about 27% of the total mass energy content of the universe, compared to just 5% for ordinary matter, the stuff that stars, planets, and people are made of. The remaining 68% is dark energy, an even more mysterious entity that drives the accelerating expansion of the universe. But despite knowing that dark matter exists, and knowing roughly how much of it there is, we have no idea what it is. We have never directly detected a dark matter particle. We do not know if it is made of a single type of particle or many. We do not know if dark matter particles interact with each other through any force other than gravity, or if they interact with ordinary matter in any way other than through gravity. It is one of the most profound gaps in our understanding of the physical world. Every galaxy, including Andromeda, is believed to be embedded within a vast halo of dark matter. The visible galaxy, the disk and bulge of stars, gas, and dust, sits at the center of a much larger, roughly spherical, or slightly flattened, distribution of dark matter that extends far beyond the visible edges. This dark matter halo provides the gravitational scaffolding that holds the galaxy together and determines its dynamics. The mass of the dark matter halo is typically many times greater than the mass of the visible galaxy. For Andromeda, the visible mass, stars, gas, dust, is estimated at a few 100 billion solar masses, while the total mass, including dark matter, is estimated at over 1 trillion solar masses. The dark matter halo is the dominant component, JWST contributes to our understanding of Andromeda's dark matter in several ways. The most direct is through the precise measurement of stellar motions. By observing how fast stars orbit the center of Andromeda at various distances, astronomers can construct a rotation curve, a graph of orbital velocity versus distance from the center. If there were no dark matter, the rotation curve would rise in the inner galaxy, where most of the visible mass is concentrated, and then fall off in the outer galaxy, following the same pattern as orbital velocities in the solar system, where outer planets orbit more slowly than inner ones because most of the mass is concentrated at the center in the Sun. But that is not what we observe. The rotation curves of spiral galaxies like Andromeda stay flat or even rise slightly at large distances. Stars in the outer parts of the galaxy orbit just as fast as, or even faster than, stars closer to the center. This can only be explained if there is additional unseen mass at large radii, mass that is distributed throughout the galaxy's halo rather than being concentrated at the center. This is the dark matter. JWST's precise observations of stellar velocities in Andromeda, particularly in the outer regions where dark matter dominates, have helped refine the galaxy's rotation curve and thus constrain the distribution of dark matter within the halo. The data suggests that Andromeda's dark matter halo is massive and extends to enormous distances from the center, possibly 500,000 light-years or more in radius. This is far beyond the visible disk, which extends only about 100,000 light-years in radius. The dark matter halo of Andromeda is so vast that it may extend a significant fraction of the distance between Andromeda and the Milky Way. And this raises a remarkable possibility. Studies have suggested, using various methods to estimate the extents of both galaxies' dark matter halos, that the dark matter halos of Andromeda and the Milky Way may already be overlapping. If both halos extend far enough, their outer edges could be touching or interpenetrating right now. If this is true, then in a sense, the collision between our two galaxies has already begun. Not in the realm of visible stars, which are still 2.5 million light-years apart, but in the invisible realm of dark matter. The dark matter halos are already interacting, already influencing each other, already beginning the long, slow process of merging that will eventually encompass the visible galaxies as well. It is a haunting thought. The merger has begun, and we cannot even see it happening. JWST also contributes to dark matter science through its observations of the tidal streams and stellar substructures in Andromeda's halo. These streams, the remnants of consumed galaxies, are not just records of galactic cannibalism. They are also probes of the dark matter distribution. As a stream of stars orbits within Andromeda's halo, its shape and structure are influenced by the gravitational field it passes through. If the dark matter halo is smooth and featureless, the stream will also be smooth. But if the dark matter halo contains subhalos, smaller concentrations of dark matter that are predicted by the leading theories of dark matter, these subhalos will gravitationally perturb the stream, creating gaps, wiggles, and density variations. By carefully mapping the shapes and properties of tidal streams in Andromeda, astronomers can search for the signatures of dark matter subhalos and test predictions of dark matter theories. This is important because different theories of dark matter make different predictions about the number and properties of these subhalos. The leading theory, cold dark matter, CDM, predicts a large number of small subhalos, far more than the number of visible satellite galaxies we observe around Andromeda or the Milky Way. This discrepancy, known as the missing satellites problem, is one of the outstanding challenges in dark matter research. Alternative theories, such as warm dark matter or self-interacting dark matter, predict fewer subhalos and could potentially resolve the discrepancy. By using tidal streams in Andromeda as probes, JWST observations can help distinguish between these competing theories. It is a beautiful example of how studying one galaxy can contribute to answering some of the most fundamental questions in physics. There is another approach to the dark matter question that JWST's Andromeda observations inform, and that is the alternative to dark matter altogether: modified Newtonian dynamics, or MOND. MOND is a hypothesis that proposes that the laws of gravity themselves are modified at very low accelerations, the accelerations typical of the outer regions of galaxies. Under MOND, there is no dark matter. Instead, the flat rotation curves and other observations attributed to dark matter are explained by a change in the law of gravity. MOND and dark matter make different predictions for the detailed dynamics of galaxies, and Andromeda, being the nearest large galaxy and the one we can study in the most detail, is one of the best places to test these competing predictions. JWST's precise measurements of stellar motions and the detailed mapping of tidal streams contribute to this test. While the current weight of evidence from cosmology and particle physics strongly favors the existence of dark matter as a real substance rather than a modification of gravity, the question is not fully settled, and every new piece of data from Andromeda adds to the evidence that will eventually resolve the debate. Now, let us come to the topic that I know many of you have been waiting for, the topic that captures the imagination like nothing else in this story: the collision, the inevitable, unstoppable, galaxy-transforming collision between Andromeda and the Milky Way. And let us talk about how JWST has refined our understanding of this cosmic event. The fact that Andromeda is approaching us was established over a century ago through spectroscopy. When astronomers split the light from Andromeda into its component wavelengths, they noticed that the characteristic spectral lines, the specific wavelengths of light emitted or absorbed by elements like hydrogen, calcium, and sodium, were shifted toward shorter, bluer wavelengths compared to their laboratory values. This blue shift is a consequence of the Doppler effect, the same effect that causes the pitch of a siren to rise as an ambulance approaches you. Just as sound waves are compressed and shifted to higher frequency when the source is approaching, light waves are compressed and shifted to shorter wavelengths, toward the blue end of the spectrum, when the light source is moving toward the observer. In a universe where virtually every galaxy is moving away from us due to the expansion of space, showing a red shift, Andromeda's blue shift is remarkable. It means Andromeda is one of the very few galaxies in the sky that is actually approaching us. And the magnitude of the blue shift tells us the speed, approximately 110 kilometers per second, directly toward the Milky Way. But knowing that Andromeda is approaching is not enough to predict a collision. To predict whether the galaxies will actually collide, you also need to know the transverse velocity, the speed at which Andromeda is moving across the sky, perpendicular to our line of sight. If the transverse velocity were large enough, Andromeda might pass by the Milky Way rather than hitting it, like two ships passing in the night. For decades, the transverse velocity of Andromeda was poorly constrained because it is incredibly difficult to measure. The apparent motion of an object 2.5 million light-years away across the sky is minuscule, even over decades of observation. But in 2012, a team of astronomers using the Hubble Space Telescope managed to measure the transverse velocity by tracking the positions of stars in Andromeda over a baseline of several years. The result confirmed what many had suspected. The transverse velocity is small. Andromeda is heading almost directly at us. A collision is virtually certain. The estimated timeline for the collision has been refined over the years as better measurements and more sophisticated models have become available. Early estimates place the collision at roughly 3 to 5 billion years in the future. More recent analyses, incorporating the Hubble transverse velocity measurements and improved models of the galaxy's masses and orbits, converge on a first close approach in approximately 4 to 5 billion years, with the galaxies passing through each other, separating and then falling back together for a second approach, eventually merging completely over a period of roughly 6 to 10 billion years from now. But these estimates depend critically on the masses of the two galaxies, and especially on the masses and extents of their dark matter halos, because it is the gravitational interaction of the full mass, dominated by dark matter, that determines the orbital dynamics. This is where JWST enters the picture. JWST's observations of Andromeda contribute to refining the collision timeline in several ways. First, as we discussed, JWST data helps constrain the distribution of dark matter in Andromeda through rotation curve measurements and tidal stream analyses. A more massive or more extended dark matter halo would mean a stronger gravitational pull and a potentially faster or more direct collision trajectory. Second, JWST's precise measurements of stellar motions provide additional data points for tracking Andromeda's overall motion. Third, JWST observations of Andromeda's satellite galaxies, particularly M33, the Triangulum galaxy, which is the third largest member of the local group, help determine whether M33 will participate in the collision as a third body, which would complicate the dynamics significantly. Some models suggest M33 will fall into the merged Milky Way plus Andromeda system, while others suggest it may be flung outward. JWST data on the motions and masses of these galaxies help distinguish between these scenarios. Let me walk you through what the collision will actually look like, step by step based on the best current simulations, refined with the latest observational data including contributions from JWST. And I want you to really try to visualize this, because it is one of the most dramatic events that will ever occur in our corner of the universe. In the first phase, starting roughly 3 to 4 billion years from now, Andromeda will begin to appear noticeably larger in Earth's sky. Over millions of years, it will grow from its current appearance as a faint, elongated smudge visible to the naked eye into a conspicuous presence, a great spiral of light stretching across a significant portion of the night sky. At this point, the gravitational interaction between the two galaxies will begin to produce visible effects. Tidal forces, the differential gravitational pull on the near side versus the far side of each galaxy, will start to distort the shapes of both galaxies. Long tidal tails of stars and gas will be drawn out, arsing away from the galaxies like the arms of cosmic dancers. In the second phase, approximately 4 to 5 billion years from now, the galaxies will make their first close approach. This is the most visually dramatic moment. The two great spirals will sweep through each other, their disks likely passing at an angle rather than perfectly head-on. But here's a crucial point that many people misunderstand. Despite the fact that each galaxy contains hundreds of billions to a trillion stars, the actual chance of any two stars colliding during this first passage is essentially zero. The distances between stars within a galaxy are astronomically vast compared to the sizes of the stars themselves. If the Sun were a ping-pong ball in New York City, the nearest star would be another ping-pong ball in Los Angeles. Galaxies are mostly empty space, so when two galaxies collide, the individual stars pass by each other like two swarms of bees merging, each bee separated from its neighbors by miles of empty air. The stars do not collide, but the gas and dust in the two galaxies absolutely do interact. Gas clouds slam into each other at high relative velocities, creating shock waves that compress the gas and trigger enormous bursts of star formation. The merged system will light up with billions of new stars forming simultaneously, a spectacular fireworks display on a galactic scale, what astronomers call a starburst. During and after the first close passage, the two galaxies will separate, their mutual gravitational pull slowing them and eventually drawing them back together. The tidal tails and bridges of stars will stretch across hundreds of thousands of light-years of space, creating a complex, chaotic, and extraordinarily beautiful structure. The second approach will be less dramatic than the first in terms of velocity, as the galaxies have lost some of their relative kinetic energy to the gravitational interaction, but the tidal disruption will continue to reshape both galaxies. Over the course of several additional passages and interactions, spanning perhaps 2 to 4 billion years, the two galaxies will gradually merge into a single, larger structure. The end result, roughly 7 to 10 billion years from now, will be the death of both spiral galaxies and the birth of a new entity, a giant elliptical galaxy. Spiral structure will be destroyed. The elegant, ordered disk and spiral arms that characterize both the Milky Way and Andromeda will be disrupted and dispersed by the chaotic gravitational interactions. Stars will be flung onto random, disorganized orbits. The result will be a large, roughly spheroidal collection of stars with no particular structure. No spiral arms, no thin disk. Astronomers have given this future galaxy the informal name Milkomeda, or Milkdromeda, a portmanteau of the two parent galaxies. It will be one of the largest galaxies in the local group, the dominant gravitational center of our cosmic neighborhood. And at the heart of Milkomeda, there will be the legacy of the two parent galaxies' central black holes. As the galaxies merge, the two supermassive black holes, Sagittarius A star from the Milky Way and M31 star from Andromeda, will gradually spiral toward each other. This process is not quick. It will take hundreds of millions to billions of years after the galaxies merge for the two black holes to sink to the center of the merged galaxy, lose orbital energy through interactions with surrounding stars and gas, and eventually form a close binary pair. Once they are close enough, they will begin radiating gravitational waves, ripples in the fabric of space-time first predicted by Albert Einstein in his general theory of relativity, and first directly detected by the LIGO experiment in 2015. These gravitational waves will carry away energy from the binary system, causing the two black holes to spiral ever closer, faster and faster, until they finally merge in a cataclysmic event that will release more energy in gravitational waves than all the stars in the observable universe are emitting in light at that moment. The merged black hole will have a mass of somewhere between 150 million and 300 million solar masses, making it one of the most massive black holes in the local universe. Now, what about us? What about our solar system, our sun, our Earth? What happens to us during this cosmic collision? The answer is both reassuring and poignant. As I mentioned, the chance of our sun, or any star, actually being hit by another star during the merger is essentially zero. The solar system will almost certainly survive the collision intact, but its location within the galaxy will change dramatically. Gravitational interactions during the merger could fling our solar system into a completely different part of the new galaxy, potentially into the outer halo, far from the familiar neighborhood of the galactic disk. We could end up in a region of space with a very different view of the night sky, surrounded by different stars, perhaps with a view of the merger's spectacular tidal tails and the bright starburst regions lighting up the sky. Then again, we could also be flung inward, closer to the chaotic, energetic central regions of the merging galaxies. Our orbit around the galactic center will be fundamentally altered, and there is no way to predict exactly where we will end up. The specific outcome depends on the exact positions and velocities of all the stars involved, a calculation that is hopelessly complex for any individual star. But here is the poignant part. By the time the Andromeda collision begins in earnest, 4 to 5 billion years from now, our Sun will be nearing the end of its main sequence lifetime. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core, swell into a red giant star, and potentially engulf Mercury, Venus, and possibly Earth. Even if Earth is not engulfed, it will be scorched by the expanding Sun, its oceans boiled away, its atmosphere stripped, its surface rendered uninhabitable. By the time Milky is settling into its final form as a giant elliptical galaxy, 7 to 10 billion years from now, our Sun will have long since passed through its red giant phase, ejected its outer layers as a planetary nebula, and shrunk into a dim, slowly cooling white dwarf. Earth, if it still exists, will be a frozen, lifeless rock orbiting a fading ember. So the collision with Andromeda is, in a sense, irrelevant to humanity's long-term survival on Earth. Earth's habitability will be destroyed by the Sun's evolution long before the galaxy merger is complete. If our descendants, or our successor species, or our artificial intelligence creations, or whatever forms of intelligence exist in our galaxy 5 billion years from now, wish to witness the merger, they will need to have long since left Earth and established themselves around younger, longer-lived stars. It is a reminder that the timescales of cosmic events are so vast, so utterly beyond human experience, that they make our civilization's entire history, all of recorded human culture, science, and achievement, look like a single heartbeat in the life of the universe. But that does not diminish the wonder of knowing. That is the beauty of what JWST has given us. We may not be around to see the collision, but we can understand it. We can model it. We can predict it. We can watch it unfold in our simulations and in our observations of other merging galaxies across the universe. We can look at Andromeda tonight, that faint smudge of light in the autumn sky, and know that it is coming for us, and feel not fear but awe at the sheer grandeur of the cosmic dance. Now, let me bring all of these threads together and talk about what JWST's Andromeda discoveries mean for the bigger picture, for our understanding of the universe as a whole. The first, and perhaps most important implication, is for our understanding of galaxy evolution. Galaxies are not static objects. They are born, they grow, they interact, they merge, and they evolve over cosmic time. Understanding how galaxies evolve is one of the central goals of modern astrophysics, and Andromeda, as the nearest large galaxy, plays a unique role in this endeavor. JWST's discoveries about Andromeda's stellar populations, merger history, star formation processes, dust structures, and central black hole environment all contribute pieces to the puzzle of galaxy evolution. And crucially, because Andromeda is close enough to study in exquisite detail, the information we extract from it serves as a calibration point, a ground truth, for interpreting observations of far more distant galaxies where such detail is impossible to achieve. This connection to distant galaxies is particularly important in the context of one of the most surprising discoveries JWST has made in its first years of operation: the existence of massive, mature galaxies in the very early universe, within the first few 100 million years after the Big Bang. When JWST turned its infrared gaze toward the deep field, looking at the most distant objects in the observable universe, it found galaxies that were far more massive, more structured, and more chemically mature than anyone had predicted for such an early cosmic epoch. These galaxies seem to have formed their stars extraordinarily quickly. assembling masses of billions of solar masses in just a few 100 million years. This was deeply challenging for existing models of galaxy formation, which predicted a slower, more gradual process of assembly. Now, how does Andromeda relate to this? Andromeda's ancient metal-poor stars, the ones JWST resolved in the halo, are local survivors from this same early cosmic epoch. By studying these ancient stars in detail, measuring their ages, metallicities, and kinematics, astronomers can learn about the conditions of star formation in the early universe and compare this with what JWST sees in the distant deep-field galaxies. Andromeda provides a local laboratory for testing theories about early galaxy formation that are informed by the astonishing distant discoveries. The two types of observations, the nearby and the distant, the detailed and the statistical, the present and the past, complement each other in ways that no single type of observation could achieve alone. The second major implication is for dark matter physics, which I touched on earlier but want to emphasize here. Every observation that constrains the distribution, amount, and properties of dark matter is valuable, because dark matter is arguably the single biggest unsolved problem in physics. We have built massive underground detectors. We have searched for dark matter particles at the Large Hadron Collider. We have looked for the products of dark matter annihilation or decay in space, and so far, all direct detection efforts have come up empty. The only way we know dark matter exists is through its gravitational effects on astronomical scales, and so astronomical observations like JWST's mapping of dark matter in Andromeda through rotation curves, stellar dynamics, and tidal stream perturbations are our best current tools for characterizing dark matter and narrowing down what it might be. Andromeda, being the nearest large galaxy and the one where these measurements can be made most precisely, is one of the most important laboratories for dark matter research in the sky. The third implication, and perhaps the one that strikes closest to the human heart, is for the question of life in the universe. This might seem like a stretch when we are talking about a galaxy 2.5 million light-years away, but hear me out. JWST's characterization of Andromeda's stellar populations, its star formation history, and its chemical evolution tells us, in statistical terms, how many stars of various types and ages exist in the galaxy, and by extension, how many planets might orbit those stars in habitable zones. With 1 trillion stars, Andromeda almost certainly contains billions of rocky planets in the habitable zones of their host stars, planets where conditions might be suitable for liquid water and, potentially, life. We cannot observe these planets directly, not even with JWST, at a distance of 2.5 million light-years. But we can estimate their numbers based on what we know about the prevalence of planets around different types of stars in our own galaxy, from missions like Kepler and TESS, and apply these statistics to Andromeda's stellar population as characterized by JWST. The numbers are staggering. Billions of potentially habitable worlds in a single galaxy. And if even a tiny fraction of those worlds harbor life, and an even tinier fraction harbor intelligent life, then Andromeda could be home to civilizations. Civilizations that may be looking back at the Milky Way right now, studying our galaxy with their own telescopes, wondering if there is anyone here. The light they would be seeing from the Milky Way left 2.5 million years ago. They would be seeing our galaxy as it was when Homo habilis was making stone tools. They would have no way of knowing that one species on one small planet in one spiral arm had developed technology and built a telescope called James Webb. And we, looking at Andromeda, are seeing it as it was 2.5 million years ago. Any civilizations there may have risen and fallen in the time it took their light to reach us. The thought is dizzying. The distances are so vast, the timescales so immense, that meaningful communication between our galaxies is essentially impossible. But the mere statistical likelihood that life exists in Andromeda, the knowledge that we are probably not looking at a dead galaxy when we look at that smudge of light in the sky, is both humbling and thrilling. The fourth implication is philosophical, and I think it is worth spending a moment on. We live in a time of extraordinary capability. We have built instruments that can peer across millions of light-years of space, that can see through walls of cosmic dust, that can decode the chemical compositions of individual stars in another galaxy, that can trace the history of galactic cannibalism through the ghostly remnants of consumed galaxies, that can map the invisible dark matter scaffolding that holds the universe together. We are the first generation of humans with this capability. For all of human history before us, the universe was a mystery beyond reach. Our ancestors could look up at the night sky and wonder, and they did wonder, beautifully and profoundly, in their myths and philosophies and religions. But they could not know. They could not measure. They could not test their ideas against the cold, clear evidence of observation. We can. And the fact that we can, the fact that a species that evolved on the African savanna to hunt, gather, and avoid predators has somehow developed the cognitive and technological capacity to build a telescope that floats 1.5 million kilometers from Earth and unlocks the secrets of other galaxies, is itself one of the most remarkable facts in the history of the universe. It is worth pausing to appreciate that. It is worth feeling the awe. Let me also take a moment here to discuss something that is easy to overlook in the excitement of new discoveries, but is scientifically essential: the context of JWST's Andromeda observations within the broader multi-wavelength, multi-messenger study of our nearest galactic neighbor. JWST does not operate in isolation. Its observations are most powerful when combined with data from other telescopes and instruments, each providing a different piece of the puzzle. The European Space Agency's Gaia mission, launched in 2013, has been mapping the positions, distances, and motions of over 1 billion stars in our own Milky Way with unprecedented precision. But Gaia's reach extends beyond our galaxy. For the brightest stars in Andromeda, particularly in the outer halo where the stellar density is lower and individual stars can be more easily resolved, Gaia has provided proper motion measurements, the apparent movement of stars across the sky, that complement JWST's observations. These proper motions, combined with JWST spectroscopic measurements of line-of-sight velocities, give a three-dimensional picture of how stars in Andromeda are moving, which is essential for understanding the galaxy's dynamics and dark matter distribution. The Hubble Space Telescope, though older and less capable in the infrared than JWST, continues to provide valuable complementary observations of Andromeda at visible and ultraviolet wavelengths. Some types of stars, particularly hot, young, blue stars, and certain types of variable stars, are better studied in visible and ultraviolet light than in the infrared. Hubble's deep imaging surveys of portions of Andromeda, particularly the famous panchromatic Hubble Andromeda Treasury (PHAT) survey, provide a catalog of millions of stars with visible and ultraviolet photometry that can be combined with JWST's infrared data to create a comprehensive panchromatic view of the stellar population. Ground-based telescopes also play a crucial role. Instruments like the Keck telescopes in Hawaii, the Very Large Telescope, VLT in Chile, and the Subaru telescope in Hawaii have spectroscopic capabilities that complement JWST's, particularly for observing large numbers of stars across wide fields of view. Radio telescopes, observing at wavelengths far longer than infrared, map the distribution of cold hydrogen gas in Andromeda, the raw fuel for future star formation. The combination of radio observations, tracing gas, infrared observations, tracing dust and embedded star formation, and visible and ultraviolet observations, tracing exposed stars and hot gas, provides a complete picture of the star formation cycle in Andromeda that no single wavelength range could provide alone. And looking to the future, the next generation of ground and space-based observatories will push our understanding of Andromeda even further. The Nancy Grace Roman Space Telescope, a NASA mission currently being prepared for launch, will have a wide-field infrared camera that can survey enormous areas of sky with JWST-like sensitivity. While JWST is like a telephoto lens, producing incredibly detailed images of small fields of view, Roman will be like a wide-angle lens, surveying large areas quickly. This makes Roman ideally suited for surveying the entire disk and halo of Andromeda in the infrared, providing a census of stellar populations, tidal streams, and dust structures across the whole galaxy that complements JWST's deep but narrow observations of specific regions. On the ground, the extremely large telescope, ELT, currently under construction in Chile by the European Southern Observatory, will have a primary mirror 39 meters in diameter, dwarfing both Hubble and JWST. While ground-based telescopes must contend with the blurring effects of Earth's atmosphere, the ELT will use advanced adaptive optic systems, deformable mirrors that adjust hundreds of times per second to correct for atmospheric distortion, to achieve resolutions approaching or even exceeding JWST's in some wavelength ranges. The ELT will be able to resolve individual stars in Andromeda with extraordinary precision and measure their properties through spectroscopy, pushing the study of Andromeda's stellar populations to an even deeper level. And in the realm of gravitational wave astronomy, the LISA mission, the Laser Interferometer Space Antenna, planned for launch by ESA in the 2030s, will detect gravitational waves at frequencies inaccessible to ground-based detectors like LEGO. LISA will be sensitive to the gravitational waves produced by the inspiral and merger of supermassive black holes, the very type of event that will occur when the Milky Way and Andromeda merge. Of course, that merger is billions of years in the future, so LISA will not detect waves from our own merger. But it will detect waves from similar mergers in other galaxies, providing direct observational data on how supermassive black holes merge during galaxy collisions. Combined with JWST's observations of the environments around supermassive black holes like M31 star, this will give us a complete picture of the black hole merger process, from the initial conditions, studied by JWST, to the final coalescence, detected by LISA. All of these observations, across wavelengths, across time, across instruments, converge on Andromeda as one of the most comprehensively studied objects in the sky. And JWST sits at the center of this web of observations, providing the critical infrared window that ties everything together. Let me now return to the core narrative and deepen some of the themes we have been exploring, because there are layers to JWST's Andromeda discoveries that we have not fully unpacked yet. Consider, for example, the question of Andromeda's formation itself. How did this galaxy come to exist? Where did it come from? The standard model of cosmology, the lambda cold dark matter model, tells us that galaxies form through a hierarchical process. In the early universe, shortly after the Big Bang, tiny density fluctuations in the primordial gas, fluctuations that originated as quantum fluctuations in the first fraction of a second of the universe's existence, and were amplified during a period of rapid expansion called inflation, served as the seeds of all future structure. Regions that were slightly denser than average had slightly stronger gravity and attracted more material from their surroundings, growing denser over time. These growing concentrations of dark matter formed the first dark matter halos, within which gas collected, cooled, and began forming the first stars. These first small systems, proto-galaxies or mini-halos, then merged with each other, growing larger and larger through successive mergers, like snowballs rolling downhill. Eventually, through billions of years of merging and accretion, these small systems built up into the large galaxies we see today. Andromeda's assembly history, as revealed by JWST, is a record of this hierarchical process. The ancient metal-poor stars in the halo are survivors from the earliest stages of assembly, either formed in situ when Andromeda was young, or brought in by small galaxies that were consumed early in Andromeda's history. The tidal streams represent more recent merger events. The detailed chemical and kinematic properties of the stellar populations in different parts of the galaxy, from the dense inner bulge to the diffuse outer halo, encode the entire history of how Andromeda was assembled, piece by piece, merger by merger, over more than 12 billion years. JWST's ability to measure the ages and metallicities of individual stars across Andromeda allows astronomers to perform what is sometimes called galactic archaeology, the reconstruction of a galaxy's formation history from the fossil record preserved in its stellar populations. Just as an archaeologist digs through layers of Earth to uncover artifacts from successively older civilizations, an astronomer can study the stars in a galaxy to uncover evidence of events that occurred billions of years ago. JWST is, in this analogy, the most powerful archaeological tool ever invented, capable of uncovering fossils that were completely hidden from all previous instruments. One of the most intriguing results from this galactic archaeology is evidence that Andromeda experienced a significant merger event approximately 8 to 10 billion years ago, when the universe was less than half its current age. This was not a minor merger with a tiny dwarf galaxy. The evidence suggests it was a merger with a moderately large galaxy, sometimes referred to in the literature as a major merger or intermediate merger event. The signatures of this event are seen in the properties of stars in Andromeda's thick disk and inner halo, regions where the kinematics and chemistry are consistent with having been violently disrupted and heated by a significant gravitational interaction. This merger may have been a defining event in Andromeda's history, responsible for building up the massive central bulge, funneling gas to the center, and growing the supermassive black hole, and transforming the galaxy from whatever it looked like before the merger into something closer to its present form. If this interpretation is correct, it means Andromeda, as we see it today, is in large part the product of a cosmic collision that happened billions of years ago, much like the collision that will occur between Andromeda and the Milky Way billions of years from now. There is a symmetry to this story, a cyclical quality. Galaxies are built through collisions, and they continue to collide and merge throughout their lives, endlessly reshaping and rebuilding. Andromeda was made by a collision, and it will participate in another collision that will unmake it, transforming it into something new. The universe is not static. It is a perpetual construction zone, where the building blocks are galaxies and the architect is gravity. Let me also explore in more depth the implications of JWST's findings about star formation in Andromeda, because this topic connects to some of the most active areas of research in modern astrophysics. Star formation is the fundamental process by which galaxies convert their raw material, the cold gas in the interstellar medium, into stars. Stars are the engines of galaxies. They produce the light by which we see galaxies. They forge the heavy elements that make planets and people possible. They drive the chemical evolution of galaxies over cosmic time. Understanding how, where, when, and why stars form is essential to understanding how galaxies work. And yet, star formation is one of the most complex and least understood processes in astrophysics. It involves the interplay of gravity, gas dynamics, magnetic fields, turbulence, radiation, and chemistry across scales ranging from hundreds of light years, the size of giant molecular clouds, the nurseries where stars are born, down to fractions of a light year, the size of individual collapsing cores that will become individual stars. No existing theory can predict from first principles exactly how many stars will form in a given molecular cloud, what masses those stars will have, or how efficiently the cloud will convert its gas into stars. We rely on observations to calibrate and constrain our models. JWST's observations of star-forming regions in Andromeda are particularly valuable because they allow us to study star formation in an environment that is similar to but not identical to the star-forming regions in our own Milky Way. Different galaxies have different metallicities, different radiation environments, different gas dynamics, and different histories of interaction and merging. All of these factors affect star formation. By studying star formation in Andromeda and comparing it with star formation in the Milky Way, astronomers can disentangle the effects of these various factors and build a more general, more robust understanding of the star formation process that applies not just to our own galaxy but to galaxies across the universe. JWST's MIRI instrument, with its ability to detect the mid-infrared emission from warm dust heated by embedded young stars, revealed star-forming regions in Andromeda that are in the earliest stages of the process, stages that are completely hidden from visible light telescopes. These are regions where dense molecular gas has begun to collapse, but the resulting protostars have not yet emerged from their cocoons of dust and gas. By observing these extremely young star-forming regions in Andromeda and comparing them with similar observations of star-forming regions in the Milky Way, which JWST has also studied, astronomers can test whether the star formation process works the same way in both galaxies, or whether there are systematic differences related to the different environments. Early results suggest both similarities and differences. The basic process of star formation, the gravitational collapse of dense gas cores within molecular clouds, appears to be fundamentally the same in Andromeda as in the Milky Way, which is reassuring because it means our locally developed models have general applicability. But the efficiency of the process, the fraction of available gas that is converted into stars per unit time, appears to vary more than expected between different regions of Andromeda and between Andromeda and the Milky Way. Some of this variation can be explained by known factors like metallicity and radiation environment, but some remains unexplained and may point to the influence of additional factors that are not yet incorporated into standard models. This is exactly the kind of observational constraint that drives theoretical progress, and JWST's Andromeda observations are contributing directly to it. Let me also spend some time discussing the detailed chemical evolution of Andromeda as revealed by JWST, because this is a topic of deep importance that connects stars, gas, dust, and the overall life cycle of a galaxy. Every star in Andromeda is a tiny chemical factory. During its life, it fuses lighter elements into heavier ones in its core. Hydrogen is fused into helium, helium into carbon and oxygen, and in the most massive stars, fusion continues all the way up to iron. When the star dies, whether through a gentle shedding of its outer layers as a planetary nebula, for low-mass stars like the Sun, or through a catastrophic supernova explosion, for massive stars, it returns a significant fraction of its mass to the interstellar medium. enriched with the heavy elements it created. This enriched gas mixes with the existing interstellar gas and is eventually incorporated into the next generation of stars, which start their lives with a slightly higher fraction of heavy elements than the previous generation. Over billions of years, this cycle of star formation, element creation, stellar death, and gas enrichment drives the chemical evolution of the galaxy, gradually increasing the overall metallicity of the interstellar medium and of successive generations of stars. JWST's spectroscopic observations of stars across Andromeda allow astronomers to trace this chemical evolution in extraordinary detail. By measuring the metallicities and detailed chemical abundance patterns of stars of different ages and in different parts of the galaxy, astronomers can reconstruct the history of chemical enrichment. Where and when did each element accumulate? How did the chemical composition of the gas change over time? Were there sudden episodes of enrichment, perhaps triggered by bursts of star formation following galaxy mergers, or was the enrichment gradual and steady? The answers to these questions are encoded in the stars, and JWST is reading that code. One of the most interesting aspects of Andromeda's chemical evolution, as revealed by JWST, is the variation in chemical abundance patterns between stars in different parts of the galaxy. Stars in the central bulge show abundance patterns dominated by the products of rapid enrichment from massive stars and core collapse supernovae, consistent with a burst of star formation early in the bulge's history. Stars in the disk show a more gradual enrichment pattern, with a significant contribution from Type 1a supernovae, exploding white dwarfs in binary systems, which produce iron peak elements on longer timescales. Stars in the halo show a range of patterns, some consistent with early rapid enrichment and others with slower enrichment, reflecting the diverse origins of halo stars, some formed in situ, others brought in by consumed galaxies with different enrichment histories. This chemical diversity is a powerful diagnostic tool, and JWST has provided the most detailed chemical map of Andromeda to date. There is an element of poetry in this. Every atom in the universe has a story. Every carbon atom in a star in Andromeda's disk was forged in the core of a previous star that lived and died in that galaxy. Every iron atom was created in a supernova explosion, a brief, brilliant flash that for a few weeks outshone the entire galaxy. Every oxygen atom was assembled, nucleus by nucleus, in the crushing pressures and temperatures of a stellar interior. And now, those atoms are arranged into new stars, new planets, new worlds, continuing the cycle that has been running since the first stars ignited in the darkness of the young universe. When JWST measures the chemical composition of a star in Andromeda, it is reading the autobiography of those atoms, tracing their journey through billions of years and countless stellar lifetimes. It is history written in the language of physics and chemistry, and JWST is the translator. Let me now delve into one more aspect of JWST's Andromeda observations that I think deserves attention, and that is the study of variable stars and transient phenomena. Andromeda is close enough that JWST can identify and monitor individual variable stars whose brightness changes over time. Variable stars are enormously useful in astronomy. Cepheid variables, as I mentioned earlier in the context of Edwin Hubble's groundbreaking distance measurement, are among the most important distance indicators in the cosmic distance ladder. RR Lyrae variables, another type of pulsating star, are excellent tracers of old stellar populations and are used to map the structure of galaxy halos. Long-period variables, including Mira variables and other asymptotic giant branch, AGB stars, are important for understanding the late stages of stellar evolution and the production of dust and heavy elements. JWST's infrared sensitivity is particularly valuable for studying variable stars in Andromeda, because many of the most astrophysically interesting variables, particularly the long-period variables and AGB stars, are cool, red stars that emit most of their light in the infrared. These are stars that are near the end of their lives, pulsating and shedding their outer layers, creating the dust that fills the interstellar medium. By monitoring these stars with JWST over time, measuring their light curves and spectra, astronomers can determine their physical properties, including their luminosities, temperatures, masses, and mass loss rates, with unprecedented precision. JWST has also contributed to the study of novae in Andromeda. Novae are thermonuclear explosions on the surface of white dwarf stars in binary systems. When a white dwarf accretes hydrogen-rich material from a companion star, the accumulated material can become hot and dense enough to ignite in a runaway thermonuclear explosion, causing the star to brighten dramatically for a period of days to weeks before fading. Andromeda produces roughly 20 to 30 novae per year, a number that is itself an important diagnostic of the galaxy's stellar population. JWST's infrared observations of novae in Andromeda can reveal the properties of the ejected material, including its mass, velocity, and chemical composition, providing insights into the physics of thermonuclear explosions and the contribution of novae to chemical enrichment. Now, I want to bring us back to the emotional and experiential dimension of this story, because I think it is important. We have been discussing science, data, observations, and theories, but at the heart of all of this is something deeply human. It is the desire to know. It is the compulsion to look up at the night sky and ask, "What is that? How does it work? What does it mean?" This desire is as old as our species. It was there when Al-Sufi recorded his little cloud in 964. It was there when Hubble identified Cepheid variables and expanded the universe. It was there when the engineers and scientists who built JWST spent 25 years of their lives, faced setbacks and doubts and budget crises, and persisted because they believed that the knowledge this telescope would bring was worth the effort. And now, when JWST turns its gold-plated mirrors toward Andromeda and collects photons that have been traveling for 2.5 million years, photons that left their source before humanity existed, and converts those photons into data that tells us about stellar populations and dark matter halos and supermassive black holes, it is fulfilling the deepest aspiration of our species. We are the universe becoming aware of itself. We are matter that has organized itself to such a degree of complexity that it can contemplate its own origins and destiny. And Andromeda, that beautiful, terrible, predatory galaxy rushing toward us through the void, is one of the grandest objects we have ever turned our gaze upon. To study it is to study ourselves, because galaxies like Andromeda are the environments in which stars and planets and life arise. Everything we are, everything we know, everything we love, exists within a galaxy. And by understanding Andromeda, we come closer to understanding the cosmic context of our own existence. Let me also address something that I think is worth discussing in the context of JWST's Andromeda findings, and that is the nature of scientific discovery itself. When we say that JWST found something shocking in Andromeda, what do we really mean? Science does not progress through a single dramatic revelation. It progresses through the painstaking accumulation of evidence, the gradual refinement of models, and the occasional paradigm shift when accumulated evidence overwhelms old ideas. JWST's Andromeda discoveries are significant not because any single finding is a complete revolution, but because the totality of the findings, taken together, represents a qualitative leap in our understanding of our nearest galactic neighbor. Each finding is a piece of a puzzle, and JWST has provided more pieces and more detailed pieces than any previous instrument. The picture that emerges is richer, more nuanced, and more surprising than what we had before. And in the world of science, that is thrilling. It means our models need to be updated, our theories need to be refined, and our understanding needs to evolve. That is how science works. That is the beauty of the process. Now, as we begin to approach the final stretch of this journey, I want to take a moment to look forward. What is the next frontier for Andromeda research? What questions remain unanswered, and how will future observations address them? One of the most pressing questions is the detailed three-dimensional structure of Andromeda. While JWST and other telescopes have provided incredibly detailed two-dimensional images, reconstructing the true three-dimensional structure of a galaxy viewed from the outside is challenging. Stars and structures at different distances along our line of sight are all projected onto a single plane, making it difficult to determine which features are in front of and which are behind others. Future observations combining JWST imaging with Gaia proper motions, ground-based spectroscopic surveys, and other data will gradually build up a three-dimensional model of Andromeda, revealing its true architecture in a way that two-dimensional images cannot.